All right, hey guys. So hopefully this will be a quick video with some recaps from last lesson and some basics about logarithms. So the first thing we did is we introduced a logarithm as the inverse of an exponential. So here we have one more example of finding that inverse relationship or function. So as you know, our first step here is going to be actually to switch the x and the y. As always, we're still going to use our SADMAP in order to solve. So the first thing I look across is I see that I can subtract the 4 to the other side. So it's going to give me x minus 4 equals 5 times 6 to the y minus 3. Now I say, okay, I add and subtracted. Is there anything I can divide or multiply? And I see that I have this 5 right here that I could divide to the other side. That gives me 6 to the y minus 3 equals x minus 4 over 5. So at this point, we've done the essay part, the SAD. Of SAD, we've moved the 4 over using addition and subtraction. Then we did the MD part, moving the 5 over using multiplication and division. And if we keep following that backwards order of operations, so we did the essay, we did the MD, we're ready to get to the exponent stage. And so here we see that the variable we want is in the exponent. That is when we use the logarithm. So this is an exponential. So in order to do that, the first thing I'm going to do is write the word log. I look across and I see that my base is 6. So that becomes my base here as well. What was the answer to my exponential becomes the argument of my logarithm. And what was the exponent becomes the new answer here. So here, notice I took an exponential, I put into logarithmic form, and in doing so, what was my exponent is now isolated. It's now on the side by itself. We have one more step of getting y completely by itself, which is adding 3 to the other side. Very, very last step within, once again, make sure that we're using this inverse notation. Our original one was y, so this is y to the negative first. Okay, so that was kind of a review of tying together our lesson from earlier. And today, like I said, we're really going to be looking at this relationship and taking logarithms slightly further. So the other part of our lesson was really looking at the relationship of an exponential function to its inverse. So the formula we've been using for exponentials is y equals a times b to the x minus h plus k. Well, when we look at this, our formula for a logarithm is going to be really similar, but slightly different. So we're still going to get y. A is still going to be in the front, times the log. Base is still the base, the b, but it's now in a different location. X is still being subtracted with h, and k is still on the outside. So very similar, but slightly different. So here we did have a horizontal asymptote, which means that for the logarithm, we have that vertical asymptote. Here, for exponentials, our domain were all real numbers. That means the range is going to be all real numbers for a logarithm. Vice versa, for the range, it was dependent on the horizontal asymptote. So now the domain of a logarithm is going to be dependent on its asymptote, but here it's a vertical asymptote. For exponentials, they will always have a y-intercept, which means that logarithms will always have an x-intercept. So especially tomorrow when we dive into looking at how to find the key features of a logarithm, once again, just to see the relationship here of that inverse. Everything dealing with the x now deals with the y. Everything dealing with the y now deals with the x. So now we can look at this. We're actually going to take this slightly further, and we're going to talk about some of the most basic properties of a logarithm. So here is one of our basic ones, and it says the log base b of b will always be equal to 1. So if we think about that, if we were to rewrite that in exponential form, our base would be b, our exponent would be 1, and it would be set equal to b. Well, this statement makes sense. B to the 1 is b. Anything to the first power is itself. So an example here in exponential form would be 3 to the first. Well, 3 to the first is 3. In logarithmic form, that would be log base 3 of 3. Well, these two numbers have to be the same. And once again, a logarithm is really asking us what exponent turned our base into our argument. So we're going to say 3 to the what equals 3. Well, that's just 1. So now every time we see this where the base and the argument are the same, we automatically know it's going to be set equal to 1. Similar here, if we were to rewrite this one in exponential form, we're going to get b to the 0th equals 1. Well, anything to the 0th power equals 1. Once again, if we do that in the examples column, we can say 3 to the 0th, when we know anything to the 0th power is 1. In logarithmic form, our base is still going to be 3. Our argument is now 1. And we're really saying, what exponent turns 3 into 1? Well, the only exponent that really turns a number into 1 is 0. So finishing that out. Okay, so if we keep moving, these two are just ones that we can always use to evaluate. These two use a little bit more thinking involved. So here it says when A is negative. So remember, A is talking about the argument. This whole statement is going to be undefined. So once again, we can think about that in exponential form. What we're saying is b to some exponent equals a negative number. Well, our base is always going to be positive. So once again, the base is always going to be positive. As I've mentioned in class multiple times, a negative exponent doesn't create a negative number. So if I have a positive number, an exponent is saying multiply by itself this many times. Well, positive times a positive is always a positive. It doesn't matter how many times I do it. So this statement is just not possible. Because it's not possible, this would be undefined. So an example of that would be saying 3, let me go back to black there, 3 to the what power equals negative 9. Well, some of you guys might want to say, oh, is 3 to the negative 2. But in reality, 3 to the negative 2 is 1 over 9. So a negative exponent causes a fraction, not a negative number. So one more time, what that would look like is a logarithm. If we had log base 3 of negative 9, we would see that and just simply say undefined. There is not an exponent that can turn 3, a positive number, into a negative number. It's undefined. This one's really similar. Here we said, well, A was negative. This one says, well, what about when A is 0? So once again, this is saying B to some number would equal 0. But let's think about this again for one more second. We're taking a positive number. So we said our B is always positive. We're raising it to an exponent, which is multiplying it by itself, and we want to try and get 0. Well, anything multiplied by itself, that's not going to be able to get a 0. The only way that would work is if B was 0, and B is always going to be a positive number, which means greater than 0. So once again, this just can't happen. There's not an exponent that would make it work. For an example, once again, we'd be saying 3 to the what would equal 0. Some of you might want to say, oh, 3 to the 0th would work. But we know that's not true because 3 to the 0th is really 1. So once again, just doesn't work. What that would look like is log base 3 of 0. We see this and we say, that's undefined. Not possible. There's no exponent that would turn 3 into 0. Okay, these two, in our next unit, when we look at our properties of exponents, which they have some really cool properties, I'm sorry, when we look at our properties of logarithms, which have some pretty cool ones, such as our properties of exponents, we're going to look at why these work a little bit more. For now, we just need to know them. So here it says log base b of b to the n equals n. So our example here might be log base 3 of 3 to the 2. I notice that my base and my argument are the same. When that happens, the exponent up here on our argument becomes the final answer. So that would be 2. Another one could be log base 3 of 27 squared. Well, when I look at this one, I go, my base and my argument aren't the same. But wait, I can rewrite 27. Log base 3 of 3 cubed squared. We know that 27 is 3 cubed. This would be log base 3 of 3 to the 6, because when you raise an exponent to an exponent, you multiply them. So this final answer would be 6. So sometimes in order to use this property, you have to rewrite your argument in terms of your base. So once again, I saw this and said that looked really similar to what we were talking about. I can rewrite 27 to be 3 to the third. This one's very similar. Notice here we had base b, argument b. Here we have base b, base b. So this is a weird one where our exponent is a logarithm. If you ever see this where your base and your base are the same, your final answer is actually just your argument. So maybe you had 5 log base 5 of 6. I see that my base and my base are the same. That means this final answer has to be 6. All right, so now that we've used all these properties, oops, nope, I thought we were going to go into some practice. We actually have one more slide of notes. Okay, so there are two very special types of logarithms. Here we've seen all the ones with all the different bases, but two of our bases are really, really important. So remember, when we did a square root, we didn't actually write the index of 2. We just knew the index was 2. That was our special radical, and it was the square root. Logarithms have two of these. The first one is known as the natural log, and the second one is known as the common log. Natural log, common log. So here, and this is going to look in log form and then in exponential form. So notice I have y and y to the negative 1, y and y to the negative 1, so we're showing their inverses of each other. The natural log we represent as ln. It is a log that is natural. So this is the only one where we don't actually write the word log. We simply say ln, log natural, ln log natural. So, and also notice it doesn't have a base written. It really does have a base. If we come down here, we can see that base is e. Now you might be going, what in the world is e? It's just a really special number like pi. It gets its own variable. It's the Euler's number. We're going to look a little bit more in some of our other things on why it works, but you just need to know it's a really special number that goes on forever. It's irrational, similar to pi. Now, it's not the same as pi, but it's a similar idea. So our natural logs have a base of e. So notice here, e to the x is the inverse of the ln of x. E to the x, a base e, is the inverse of the natural log. The other one we have is the common log. Once again, notice there's no base written. That's because the base is really 10. You may have heard that we have a base 10 number system. A base 10 number system means that once we hit 10, we start over. Because of that, base 10 is the most common. So once again, the log of x, if there's no base written, and it's not an ln, just normal log, no base written, that base is really 10. So let's look at an example. Here, if I had e, let's just do e to the x equals k. In order to write this in exponential form, in logarithmic form, we would typically start with the word log. But when I see that my base is an e, I go, oops, that's the natural log. So instead, I'm going to write ln. Now remember, I write my l's as cursive L, so this is just an L. So this is just ln. I do not write the base. Writing ln automatically says that the base is e. What was the answer still becomes the argument, and what was the exponent still goes in a side by itself. We need another one over here. We can say 10 squared equals 100. In order to write this in logarithmic form, I am going to write the word log, and then I see that it's base 10, and I say, you know what? We don't have to write a base 10. Just like for a square root, we don't write the square. We don't write the index. Just for an exponent of 1, we don't write the exponent 1. For a logarithm base 10, we don't write the base 10. What was the answer still becomes the argument, and what was the exponent still goes on the side by itself. Alrighty, so these are kind of our big pieces. These are our properties. These are some of our specials. So we have a special type, a natural log. This may be really important when we get into applications. And then the common log. So if your base is 10, you just write log, no base. If your base is the special number e, you actually write ln for natural log. All right, so let's just do a little bit of evaluating here. So one of the things I have written here is, remember, the answer represents the exponent. So each of these times we're going to ask ourselves, what was the exponent that made this true? I recommend pausing at this point, trying some of these on your own, and then starting again. So as we look at this, I'm going to say, okay, 3 to the what? And some of you guys might want to write this. Please do not use X here, but if you want to use a question mark to kind of help you, we're going to say 3 to the what is 27. This is what we're really trying to figure out. Well, 3 to the third is 27. So this just equals 3. Notice I did not say x equals 3. There's no x in my original, so I'm not going to put an x in my final answer. We're simply going to evaluate. Once again, we're going to say 2 to the what equals 16? Well, 2 to the fourth equals 16. 4 to the what equals 16? Well, 4 squared equals 16. Hopefully you're starting to see this pattern. These ones were all relatively simple, as our base was a whole number, and so was our argument. Even more, our base was kind of small, and our argument was larger. So we know that a small number to an exponent is going to give us a larger number. This next column is going to look a little different. Here, I'm saying what exponent turned 125 into 5? So once again, I might want to write this out. 125 to the what equals 5? Well, I know the cubed root of 125 is equal to 5, and the cubed root can be rewritten as 1/3, a fraction of 1/3. So my answer here is going to be 1/3. 125 to the 1/3 power equals 5. That's because the cube root of 125 is 5. This one looks a little similar, but different. So notice this one we need a large base and a small argument. Here we still have a small base, but our argument is a fraction. So once again, we're going to say 6 to the what equals 1 over 216. Well, I know in order for a normal number to be turned into a fraction, my exponent has to be negative. 6 cubed gives me 216. So my answer here is -3. Once again, the negative is what created the fraction, and 6 cubed gave me the 216. I look across here and I go, oh, there's not a base. But I know when there's not a base, it's really a 10. So I'm saying 10 to the what gave me 100. We actually just saw this on the other slide. It's 2. All right. Oh, this was one of ours. We're saying 8 to the what equals 8? Well, we know that's just going to be the first power. Here we say 5 to the what equals 1. Well, we know that's the 0th power. And those two were two of our properties. This one, the ln of 2, well, here we're saying e to the what equals 2. This is actually one that we wouldn't be able to evaluate without a calculator because we don't actually know e to the what equals 2. So to show you the rewrite here, this is one that actually to evaluate it, you would need your calculator. And in the next unit, every once in a while, you will be able to use your calculator on these. So from here, I have some last few takeaways. It's really going to come into this area. So some of the last big takeaways you need. Here, you should be able to do this again. Log base b of b is always 1. Log base b of 1 is always 0. This one, ooh, is a little tricky. But if we think about it, the base is e. So the ln of e, this would be the base, and the argument are the same. It's really the same property. So it's going to equal 1 as well. Here, we talked about this on the last slide. We said the argument has to be positive. The argument of a logarithm must be positive, and we saw why that worked in an earlier slide. So anytime the argument is negative or 0, we're going to call that undefined. This is going to be important in finding our vertical asymptotes. This one, hopefully you saw on the last slide. If the argument is a fraction, the exponent is going to be negative. So once again, if we're creating an argument that's a fraction, or really, this should really super say, if the argument is a fraction, or if the base is a fraction, that's most likely because an exponent is negative. So when one of them is a fraction, that's because our exponent was negative. Here, if the argument is smaller than the base, that means the exponent is a fraction. So once again, I'm going to call this number 1, so we can just do a quick little example down here. Log base 3 of 1 over 27 would be negative 3. My base was a whole number, my argument was a fraction, so my exponent was negative. Versus if I call this 2, I'm going to say log base 81 of 3, this is going to be 1/4. We're saying the 4th root of 81 gives me 3. The 4th root of 81 gives me 3. So that's just showing these two again. I'm going to put this one here. Go ahead and copy it down into your notes. And this is one I'll actually talk to you guys a little bit more in class because this is going to be super important as we move into the next unit. So there you have it. These are some of the basics of logarithms. After this, you need to be super confident in evaluating logarithms. You need to understand your rules here, these basic properties. You need to know that the argument of a logarithm must be positive. This is going to help you with your evaluating seeing this pattern. All right, and with that, we are done with our small little mini lesson, and you guys are moving into some practice.